Hey, good morning, everybody. Today we're going to talk about the law of multiple proportions. We're also going to discuss empirical and molecular formulas. And really what we're going to be looking at is kind of the power of ratios and how can we use these math ratios to figure out some new different things about these compounds. So let's jump into it here. Last time we talked about the law of definite proportions, which essentially says that every time that we make water, regardless of if it's a small puddle or a whole bathtub full, the ratio of hydrogen to oxygen will always be the same because water is only created one way. You need two hydrogens for every one oxygen. Now, the law of multiple proportions suggests that if we have combinations of those same elements, say hydrogen and oxygen, but we have a different compound that's not water, well, then the ratio of H's and O's will be different than that of water. And that makes sense. If we have a different compound or different molecule, we would expect that the chemical makeup needs to be different. So we're going to have a different number of atoms, and therefore the ratio of their masses are going to be unique to that compound. Let me give you kind of a picture and talk that through. Let's say that we have five different compounds, and we know that all five of them have some nitrogen and oxygen. That's it. That's the only two or elements in these compounds. And if all five of our unique compounds have 14 grams of nitrogen, what would you suspect needs to be true about the grams of oxygen in each? Well, if we have five different compounds and they have the same amount of nitrogen, well, to be different from one another, we would expect that these grams of oxygen be different from one another. And that's really all the law of multiple proportion says, that each unique compound has its own unique combination of masses per element. Now, if we dive into this a little bit further, though, if we know something about one of these compounds, we can kind of multiply and divide and do some ratios and actually figure out the composition of some of these other compounds. So let's take a look at that. Take a look. When we have same amount of nitrogen, right, 14 grams in each, we do have different numbers here, but these numbers aren't random and awkward and odd, right? There's something to do or sort of a pattern, right, that's evolving. Hopefully you can see that these are all kind of multiples of these 8 grams. Well, why is that? Well, that comes with these sort of fixed ratios of elements in the compound. Let me kind of show you what I mean by that. So this is the same table, and I'm going to give you a little cheat sheet. I'm going to say that according to percent composition and kind of assuming a particular size sample, let's say we have a compound of nitrogen monoxide. There's only one nitrogen, one oxygen. And if we look at the sort of grams ratio here, for every 14 grams of nitrogen, we would have 16 grams of oxygen. Well, even though we don't know these chemical formulas, we can use this information and actually figure out what these chemical formulas are. Let's take a look at this one right here. All right, and I'm going to kind of go out of order, and hopefully this makes sense, right? So we can see that this 14 to 16 ratio over here yielded a 1-to-1 ratio of the elements in the chemical formula. Let's take a look down here. We've got that same 14. Keep this in mind. This 14 being common is kind of important here. But now we have sort of double the amount of oxygen that we had in that 1-to-1 ratio. So if I kind of look at that proportionally, now I'm looking at a 1-to-2 ratio. For every 1 part nitrogen, I'm going to have twice as much oxygen as I had in this compound here. With all that being said, what would you kind of conclude about this chemical formula? In order to have twice as much oxygen, we would need twice the number of oxygen atoms that are in this chemical formula. Since there's only one oxygen here, by default, we would need to have two oxygens. So this would be the ratio, a new compound, right? A different ratio and a different setup of the masses here for nitrogen dioxide. All right, let's look kind of back at the beginning here. If you'll look and kind of compare this to our 1-to-1 ratio, you'll see that this compound number one has half of the amount of oxygen. If we look over here and try to apply, like, well, maybe the chemical formula is N10.5. I hope you remember that we can't have decimals as subscripts. They represent the actual number of atoms that are kind of attached in that chemical formula. But this ratio can still be true, but we need whole numbers. So how do we kind of keep this same ratio, but still end up with a chemical formula that has whole numbers? You can always multiply ratios by whole numbers. Usually 2 is a good place to start and go from there. So if I were to multiply this 1 to 0.5 ratio by 2, right, I would say, or I would get to a 2-to-1 ratio. That's the same kind of proportionality, but being whole numbers allows me to kind of apply that to the chemical formula. So half as much oxygen, right? So we have that ratio that's 1 to 1.5, excuse me, 1 to 0.5. But in order for us to apply that to subscripts, we need to be whole numbers, so we can always multiply that by 2. If we look, right, compound 3, again, I'm going to kind of compare that to compound 2 here, has the same amount of nitrogen, but it has like 1.5 times the amount of oxygen. So we have this 1 to 1.5 ratio. Again, we can't have decimals in the subscript, but I could multiply this by 2. That would give us whole numbers here, and we would have an N2O3 ratio. And finally, we can look at this 1 to 2.5 ratio, again, relative to compound 2 and 5 is what we're comparing here. We can multiply those. So all the law of multiple proportions says is that if we have 5 different compounds that are made up of the same elements, then in order to be unique in different compounds, we have to see 5 different sort of ratios between their masses. But the law of definite proportions says that even though they're different compounds, they're going to have some sort of similarities if we can sort of keep something common for them. In this case, it's going to be the grams of nitrogen. All right, so let's take a look at a way to use percent composition to kind of also work through this. So I'm going to give you kind of a hypothetical example. We're going to talk about carbon monoxide. So we know this compound, carbon mono prefix meaning one. There's one carbon, one oxygen. And if I were to sort of do the percent by mass, right, the percent composition, we've already talked about that. This particular compound is 57.1% oxygen and 42% carbon. Now, there's an unknown molecule. What I do know is that this unknown molecule is going to be made up of just carbons and just oxygens, but I don't know what the ratio is. I don't know how many C's and I don't know how many O's there are. So giving you a cheat sheet, kind of giving you some additional information, this unknown molecule with unknown formula is 72.7% oxygen and 27.3% carbon. Our goal is to figure out what is this chemical formula? How many C's will there be? How many O's will there be? Okay, obviously it's different because the proportion by mass is different, so it's not the same compound. So how can we sort of get to compare these? What would be easy? Percent composition is easiest if we kind of assume that 100-gram sample. And again, we do that because we make the percentages equal to the gram amount. So you'll notice that this chart here is filled in with just the gram equivalents of the percent compositions. Now, in the last example, all the compounds had 14 grams of nitrogen. Let me flash back to that really quickly to kind of show you how this is different. So everything here had 14 grams of nitrogen. If we look at our 2 new compounds here, we see that they don't have the same amount of oxygen and they don't have the same amount of carbon. So I'm going to have to do a little bit of work to sort of create this equal like ground, this comparison between these two. So how would I do that? If I don't have the same number of grams of carbon, grams of oxygen, like how in the world could I determine what the chemical formulas are? So this is a super important step. It's not going to be sort of said in the question. This is something you're just going to need to know how to do. We want to create a ratio between the two elements, the carbon and the oxygen, for these two compounds, and then you're going to see how they compare. I get asked this a lot, like, how do you create the ratio? The easiest thing I can suggest, just take the bigger number and divide it by the smaller number. Now, you need to be consistent. So, like in this particular compound for the carbon monoxide, the bigger number is grams of oxygen divided by the smaller number grams of carbon. Over here, we're going to need to follow that same order, the oxygen divided by the carbon. Again, it's bigger divided by smaller, but it's more important that it is O divided by C, O divided by C. So again, I'm creating a ratio between the two elements. And you'll notice here that the outcome of that has something in common. Now, how do I read this ratio? What I'm literally doing is the grams of oxygen divided by the grams of carbon. Now, what does this answer mean? Right? Well, that means that there are 1.33 grams of oxygen per every 1 gram of carbon. So we're creating that ratio relative to 1. When we do it for the unknown compound, we can see that it has 2.66 grams of oxygen per every 1 gram of carbon. Now you should see that this is just like the previous problem where everything had 14 grams of nitrogen. Both of these have something in common, have 1 gram of carbon. So when there is 1 gram of carbon, what do you notice about the sort of relative amounts of oxygen? And it's pretty easy to see here that the new compound has twice as much oxygen. Well, what if it's not like super friendly numbers, right? How do we figure out what that ratio is? You would just, again, take the bigger number, divide it by the smaller number here, and we can see again that the bigger compound has twice as much oxygen as the carbon monoxide does. Okay. Remember, we know what the chemical formula of carbon monoxide is. That was given to us. And what we've concluded is that this unknown this unknown compound has twice as much oxygen with the same amount of carbon. Okay. So how many carbons did the carbon monoxide have? Just one. So our new molecule has to have just one carbon, but the new molecule, the unknown, has twice as many oxygens. So what would you suspect to see over here? hopefully, again, CO2, and that's carbon dioxide. So again, if you are given some strategic information and you can create these ratios, this common ground where they both have 1 gram of carbon, we can apply the ratio of the other elements to determine what the chemical formula is. And that's really related to what we're going to talk about quickly. Now, you should have done empirical molecular formulas in the past, so I'm going to kind of breeze through this, but the empirical formula represents the simplest whole number ratio of the elements in the compound. Essentially, right, what we can boil the subscripts, what's their ratio at best. We do this with ionic compounds a lot, but we don't do it with covalent molecules because of this. The prefixes help us determine what the chemical formula is. So again, the empirical represents the sort of most reduced chemical formula. So H's and O's. With this 1-to-1 ratio, it can't go down any further. Well, that's actually the empirical formula of hydrogen peroxide. Okay, this is the actual chemical formula for hydrogen peroxide, and we call that the molecular formula. That's the actual numbers of elements that make up the compound. Okay, sometimes the empirical and molecular formulas are the same, but they're not always. And so that's what we're going to kind of talk about here. Okay, so you need to know the definition between these two. We're going to talk a little bit about how you solve for each. Let's consider this problem. A chromium-containing compound is found to be 68.4% by mass. I believe that's chromium by mass, if I cover myself up. If the remaining mass is only oxygen, what would the empirical formula be? This is a process that you need to be familiar with. The way you determine the chemical formula is through the ratio, specifically the mole ratio of those elements in the compound. So let's consider what we are given. We have the percent compositions of each of these, but we want to create a mole ratio. Well, how do we get to moles? Well, we got to get from grams and then convert that to moles. So the first step here is, how do I go from percentages to grams? This is our trick. If we assume 100-gram sample, then we are going to make these percentages into the gram amounts. So that's rule number 1. Rule number 2 is I need to create a whole number mole ratio. So how do I do that? All right, we're going to take the grams and we're going to convert it to moles using the bridge that's between them, which is the molar mass bridge. So we would look on the periodic table and find this right here. This is the atomic mass of the individual element. So this was given to me in the problem. I'm going to divide it by the molar mass of chromium on the periodic table, and I got 1.315 moles of chromium. I'm going to look at that for oxygen really quickly here. Empirical formula is one of the few times that we do not mess with diatomic molecules. So yes, oxygen is diatomic when we write chemical formulas, but when we're creating these whole number ratios, we just want the mass of a singular individual oxygen, right? So that's 16. So this is given to me in the problem, and then we're going to divide it by the molar mass 16 here, okay? So we have now the quantity of moles for both of those. We're going to create now a mole ratio between these two. How do I do that? Remember, it's going to be the bigger number divided by the smaller number. We're going to take the mole quantities for each of these two numbers. We're going to divide them both, right? Divide them both by whichever one happens to be smaller. So which one of these two mole values is the smallest? And that's going to be the chromium. So that's going to leave something with 1. That's okay, right? A chemical formula, one of the elements is going to have a subscript of 1, and that's we want that to happen. Now, the other one over here has this ratio of 1.5. Now, normally, again, these whole number mole ratios can become the chemical formula, but we just got done talking about this, that we can't have decimals as part of the chemical formula. So how do I keep this 1 to 1.5 ratio, but not have a decimal? And again, this is where we can multiply something by 2. Those ratios can always be multiplied. It'll still be 1 to 1.5, but when we multiply them both by kind of an even number here, we are allowed to get that sort of 2 to 3 ratio, and that's what the subscripts are going to be in the chemical formula, okay? Now, the molecular formula is a related to but kind of similar process. The molecular formula gives you the kind of actual chemical formula for what the compound is. And again, that simple kind of empirical formula, the most reduced form, is always going to be related to the actual chemical formula by some whole number multiple. So consider glucose, C6H12O6. If I were to sort of divide all these by 6, the subscripts there are, we're going to get this empirical formula, right? 1 to 2 to 1 cannot be reduced down any further, and that's the empirical formula. This is the actual formula. The trick here to kind of go from the empirical to molecular is really seeing that same ratio apply to the molar mass of the compound. Now, this 30 came from adding up the mass of 1 carbon, 2 hydrogens, and 1 oxygen. So the molar mass, 12 plus 2.02 plus 16 equals this 30. The molar mass of the 6 carbons and 12 hydrogens and 6 oxygens is 180. Now, we said if we kind of look, if we divide the subscripts by 6 to get the chemical formula, what do you notice is happening about the ratio between the molar mass of the compound and the molar mass of the simplified empirical formula? It's also divided by 6, and that's no accident. So what we do to the empirical formula, we need to do to have the same ratio apply to the molar masses. So again, if we're trying to figure out what that is, we can either divide, or really to figure that out, we take the molar mass of the compound, we divide it by the molar mass of the empirical formula. Whatever that ratio is, we can kind of work backwards and multiply these subscripts by that same ratio to get the actual subscripts for the chemical compound. Let's do one practice problem together here. The elemental analysis of lactic acid. So they're going to give us the molar mass that 90 grams has an empirical formula of CH2O, right? So these two things are not they're related, but they're not the same thing. So our goal is to figure out the actual chemical formula, right? So it's some iteration of this, right? But we don't know, is it twice as big, 3, 4, 8 times as big? Okay, we don't know that. So again, the hidden trick here that you've got to figure out is to figure out what the molar mass of the empirical formula is. So they gave us this. And so I could figure out the empirical formula by doing that same molar mass. One carbon is 12. I've got 2 hydrogens. So 1 times, or 1.01 times 2 gives me that value. And the 1 oxygen is 16. So the empirical formula is 30 grams. Now here's the trick. How does that empirical mass relate to the actual molar mass of the actual lactic acid compound? And again, I hope you can see this. If you don't know if it's kind of weirder numbers, you can always create that ratio of the bigger number divided by the smaller number. But what we're seeing here is that lactic acid is actually 3 times bigger than the simplified version, right? So if we know the chemical formula for the simpler version, and we know that the actual compound is 3 times bigger than that, we can apply that ratio. We're going to multiply all the subscripts by whatever the ratio number is, 3 in this case. So we need 3 times as many carbons, we need 3 times as many hydrogens, and we need 3 times as many oxygens. And so all we simply do is multiply the subscripts by 3, and we have the correct chemical compound for the actual compound. Now, if you've got a minute, you can check your work here. The actual molar mass should be 90.08. So take a second and you can check your work. 3 carbons, 12 times 3 plus 6 times 1 for the molar mass of the hydrogen, and 3 times 16 for oxygen. That should equal 90. If it doesn't, then you have not done this calculation correctly. So this is an easy way to double check your work. Don't just assume that your ratio is right. Take a look at your answer and kind of work and see if you can actually calculate that molar mass. All right, that's it for today. I hope you helpful. If you have any questions, feel free to email me and we'll talk more about this in class. Thank you.